Let us look at the circuits of some of the most popular dc-dc converter circuits and also the most fundamental ones. The circuit shown here has two switches, S1 and S2, and one inductor and capacitor, L and C. Vin is the input voltage, and the voltage across this capacitor and of course the resistor is the output voltage VO. This is known as buck converter or step down converter because the output voltage, the average value of output voltage is always less than the input voltage. We will see how it is. In fact, this circuit can be seen as half of the bridge circuit that we have seen in our very first lectures, and with an additional inductor and capacitor. The second converter that is shown here is known as boost converter, which is also step up converter. What do you mean by this? That the average output voltage is always more than the input voltage. And how do we realize this converter? It can be seen as the rotation of these three terminals X, Y, Z marked in the buck converter circuit. So if you rotate them such that X comes here and Y comes here and Z comes here, we realize a boost converter. And boost converter can also be seen as an offshoot of bridge circuit that we have discussed in the beginning. So we have a bridge circuit, but then the inductor position has changed from here to here. So if you change the inductor position and also the connection of input and output, buck converter becomes boost converter as shown here. If we rotate the three terminals X and Y further, three nodes X and Y further, then we can realize something called buck boost converter, which has the ability to give a voltage, the average voltage at the output being less than the input voltage or more than the input voltage. However, the polarity of the output voltage will be negative, inverse of the input voltage, as we shall see soon. We can replace the inductor in this buck boost converter circuit by a transformer. And why can we do that? Because if you recall the equivalent circuit of a transformer, it has series resistance, the primary resistance and primary leakage inductance, then you have a magnetizing inductance, then you have secondary resistance and secondary leakage inductance. So in an ideal transformer, leakage is 0, so this inductance is not present, and there are no resistances for the windings, so this is also 0, this is also 0, and the magnetizing inductance is infinity, right? So in a practical transformer, well designed transformer, the leakage inductance will be much smaller than the magnetizing inductance. So we can bring in the transformer in the place of an inductor, and if we do so, we result in this circuit. So we have a switch on the primary side of the transformer, and we have another switch on the secondary side of the transformer, followed by a capacitor and a resistor. So this circuit is popularly known as flyback converter. It is an isolated dc-dc converter as evident from the circuit. The input and output do not have a common terminal. There are many other types of dc-dc converters. For example, you can have multiple inductors and multiple capacitors, and one can design a dc-dc converter with more number of switches, and some of the switches can be fully controlled and some of them can be diodes, but there should be at least one fully controlled switch as mentioned earlier. And how do we decide which switch is going to be fully controlled and which switch can be an uncontrolled switch like diode? Let us consider a circuit of buck converter. S1 and S2, there are two switches. We want to know what can we replace them with, because ultimately it has to be MOSFET, IGBT or a diode. So this choice again will boil down to looking at the voltage blocking capabilities and current carrying capabilities. And how do we know them? If we analyze the circuit and look at the currents and voltages across switches, current flowing through the switch and voltage that is appearing across the switch, when it is off, we will know the current carrying capability requirement and voltage blocking capability requirement. Based on that, we can choose whether it can be MOSFET or an IGBT or a combination of them, or just a diode would be enough. There are many types of dc-dc converters that are being used in a variety of industrial applications. So what is the difference? Let us say we have an application in which we need to choose a particular dc-dc converter to perform some kind of step down or step up or inversion of polarity, some function. For that we have 2-3 kinds of options. For example, you take buck and buck boost. Buck boost can also do buck, the step down operation. Buck converter can also do step down operation, right? So how do we choose that? We choose it depending upon again the performance. So we have to go back to the performance metrics of a power converter that we have discussed, and we look at different metrics. We can look at the cleanness of waveforms, how clean they are, or we can look at the size of the magnetic components, whether we need a smaller inductor for one power electronic converter or not, or we can look at the EMI, the electromagnetic interference, or we can look at the regulation, how regulated the output voltage would be, which gives a tighter regulation, which converter gives a tighter regulation, and then sensitivity to disturbances. If some disturbance occurs, for example, the input voltage has suddenly changed, and how well the converter can maintain the output voltage as desired. And of course the efficiency, which converter is more efficient in the whole range of operating points of interest, and so on. However, as already mentioned, in this course we are only looking at the steady state operating conditions, and we want to look at the cleaner waveforms and also predict some losses using the idealized waveforms. So as far as this course is concerned, we are only interested in that particular performance metric. So we'll try to understand how to obtain the waveforms of different voltages and currents in a dc-dc converter under periodic steady state, and that we will learn by analyzing these fundamental circuits, and the same analysis can be applied for any DC to DC converter.